Everyone, and welcome to Groundwater Talk Live. I'm Tom Ballard, the groundwater guy, and um, today we're going to talk about wire to water efficiency because pumps and motors are really the lifeblood of your water system, and you got to know how efficient they are, how close they are to failure, and when you're going to need to upgrade them, overhaul them. And wire to water efficiency is a great way to get at that, but there are uh, some difficulties in getting to the calculations, and so we're going to demystify that today as we get into wire to water efficiency. So let's kind of dive in today here and really talk about this because you'll find there's a number of people out here that will go around and actually do this for you, but you can actually do the calculations yourself if you got the data. And that's what we're going to talk about today is how you do the calculations, and this is part of our data driven trend is really to get at the data we need to really efficiently manage our water utility. And the efficiency of our pumps and motors is a critical part of that, really. So that's what we're going to dive in today. So let's dive into the presentation here and go from here. So we're really looking at how we improve our efficiency and reduce costs. So this is going to be our comprehensive guide to water efficiency and water supply well pumps. And so we're going to look at how we calculate that, how we analyze it, and really how we optimize our pumps and motors. And it's really to get at how efficient our pumps and motors are running so we know it's part of our asset management plan really is so we understand how close they are to failure, and so we can basically develop some trends here. And like all the things we do, if you've seen any of my other shows, you know I'm really big on calculating these trends, and that's going to be part of that. Is wire to water efficiency. You want to calculate that regularly and track it because that's going to tell you when you're going to need to do maintenance or do replacement on your pumps and motors. So, all right. So, the definition. What we're going to talk about today is really the definition of wire to water efficiency, what it is, why it matters, the importance of it to your operation. We've talked about that a little bit. The calculation methods. We're going to look at a case analysis and results interpretation, optimization strategy, best practices, and if you got any questions, you can feel free to leave those in the chat, and we'll answer those for you as well. So, all right. So the core definition is really wire to water efficiency is really a comprehensive metric measuring how effectively an electromechanical pumping system, and that's your pumps and motors, converts electrical energy input into useful hydraulic power output. So that efficiency is what you're going to be measured through wire to water efficiency. And that's going to get at how well your system is running. And as we see, as we follow our trends, we can determine then when we're going to need to do uphauls and or overhauls and upgrades to our system. Key components measuring the entire system, not just the individual components. So how everything works together. It includes the motor, the pump, VFD if it's equipped. It's expressed as a percentage, generally somewhere in the range of 60 to 80%. You're probably not going to see anything much over 80%, even in a brand new system, because it's important to understand, and we'll look at this down below, is that it's more additive and not a product. So what we're really looking at is energy conversion. So our electrical output, the energy conversion to our hydraulic output. So here's what's important to understand is the common misconception is that the wire to water efficiencies are an average of individual efficiencies. So the pump and the motor, you add them together, you divide by two, you come up with an average, and maybe you come up with, if you have 85% and 90%, you come up with 87.5%. That is incorrect. It is a multiplier. It's a product of the individual efficiency. So you're going to get a number a little lower than you might be expecting, but that helps determine what your efficiencies are. So you're really multiplying the motor efficiencies, by the pump efficiencies, and that's going to get you to at your actual wire to water efficiency. So this is a common misconception, and people need to understand, and this is where they go wrong in the calculations and wonder what they're doing wrong. So it's not an average; it's a product. So why wire to water efficiency matters? It's really a critical measure for water supply system pumps, which are is really the heart of our system. Whether you have a water supply well or whether you're pumping from surface water storage, it's going to be an important part of your system because if your pump is not working efficiently, then your whole system is going to suffer from that. So the wire to water efficiency is going to get us some valuable insights into multiple dimensions. So first is energy cost management. Obviously, pumping systems are major electricity consumers and water utilities, so efficiency improvements in those pumps and motors is really going to directly translate to operational cost reduction. Real performance assessment, so it provides a comprehensive indicator of actual system performance under real world condition, revealing gaps between design specifications and reality. But really it's a real time and a real and important measure that you can track by trends, like I mentioned, and the trends are what's important here. Equipment selection. This helps us determine the right to select the most suitable pump, motor, control systems, how they work together, and ensure optimal performance at required operating conditions. Environmental impact. Higher efficiency means reduced energy consumption and lower carbon footprint if you're interested in that. And so you can say you're supporting sustainable goals in the water sector. System optimization. We want our system to be optimal. The pumps and motors are part of that, they're a key part of that, but we really want to optimize our whole system. And this is really looking at a key component to optimizing our entire system. So the key takeaway is wire to water efficiency provides basically a holistic view of your pumping system's performance, helping you make data driven decisions for operational excellence. So that's really what we're looking at is an overall view of your pumping system's performance here. So, symptoms of low efficiency, you're going to have high energy bills, and that's basically your direct sign of inefficiency. Pumps running at less than optimal efficiency consume significant more electricity than more optimally calibrated pumps. So you're going to have higher operating costs. That's a direct way to save money. The frequency of maintenance. Pumps operating at non-optimal efficiency points really are going to require, they're going to have more mechanical stress, and you're going to lead to more frequent maintenance on those pumps. And that is going to cost you money and downtime. Noise and vibration, pumps that aren't optimally maintained are going to be noisy. They're going to create vibration. That's going to, it can increase in things like cavitation, but it can also affect other parts of your system too if you have a lot of vibration. Performance issues, difficulty reaching expected flow rates or pressure targets because of inadequate power output, or despite adequate power output means your pumps aren't operating efficiently. So you're getting enough power to those pumps, they're not operating optimally. There's something wrong with the pump, and so that's where wire to water efficiency comes in. So excessive throttling, valves that are severely throttled to control flow creates significant energy waste. This practice reduces system efficiency and increases wear. You're better off going with a VFD within range, or basically sizing your pump according to your system. We see people way oversizing the pumps, throwing a VFD on it, and that's just not a good combination. You want to properly size your pump and motor and put a VFD on there that's going to operate within the range you need it to operate. And that's going to make things a little more optimal too. That's going to be reflected in your wire to water efficiency as well. Clogged screens, blocked intake screens, or air pockets and pipes increase the workload for pumps, creating inefficiencies and reduce system performance. You can get at that through wire to water efficiency calculations as well. So, Change up my slide here. Okay, so here is our core formula for wire to water efficiency, and that's going to be expressed as a percentage. So it's going to be your water horsepower divided by input power times 100%. So that measures the energy conversion efficiency from electrical input to hydraulic output. Very important. So there's two components to that. There's the water horsepower, which is going to be flow times total head divided by the constant of 3960. So the flow is going to be in gallons per minute. The total head, and it's going to be important to note here, even though it doesn't say it here, this is going to be total dynamic head. We'll see how to calculate that in a coming slide. That's going to be in feet, and our constant, which is dimensionless, is going to be 3960. Now, your input power, which is your horsepower, is going to be your input power in kilowatt hours divided by 0.746. Once again, a constant there. So your input power is in kilowatt hours. Your constant is kilowatt hours per horsepower, 0.746. This converts electrical power to mechanical power. So the combined formula is flow times total dynamic head divided by 3960 times the input power times 100%. So there's our calculation. Um, so what we're doing here, and I guess I'm a little cut off, but this is the step-by-step process here. So sorry about that. A little cut off on the top. It is some formatting issues there. So number one, we might want to measure the input power. So you can use a portable power analyzer or your SCADA system to measure the input electrical power, kilowatt hours, at the motor or the VFD input. Ensure that there's no other electrical loads like HVAC or lighting are included in the measurement. So you want to be able to separate those out. So it's good to meter those separately, or at least have a separate connection where you can measure that. So two, determine the flow rate. Read the flow rate gallons per minute from a calibrated flow meter installed on the discharge pipe. Ensure the flow meter is properly calibrated for accurate readings. This is probably the easiest part because most everyone has an accurate flow meter, but you want to make sure that's properly calibrated and so you can get an accurate reading if you really want to dial this in. So now we're going to calculate the total dynamic head by adding suction head and discharge head. So your total dynamic head equals your discharge pressure, PSI, times 2.31, plus the suction vacuum in inches of mercury times 1.13. Lastly, next you're going to compute the water horsepower using the formula water horsepower equals flow times total dynamic head divided by 3960. And then your wire to water efficiency is water horsepower by input power and multiply by 100 to get the efficiency. So that's going to give you your efficiency percent. And once again, remember, accurate data collection is critical, garbage in, garbage out. And remember, this is going to be a product, and it's not an average, it's a product of these two efficiencies we're seeing here. All right, so understanding total dynamic head, that is the head. The total head we're looking at is total dynamic head. So there's a little bit of difference here. It's the static pressure difference, the vertical distance from the pump suction to the discharge point, takes into account friction loss through pipes, elbows, valves, and your discharge pressure head. Pressure is needed at the discharge point. So your total dynamic head formula is TDH equals discharge head pressure plus suction pressure head. So field measurements are going to be measure suction pressure, vacuum for well pumps, measure discharge pressure, convert the pressure to feet of head. And then so your critical conversion constants here are 1 psi equals 2.31 feet ahead. So a lot of pumps we see now basically have a air tube to measure the psi, and they're actually using this to calculate static and pumping water level because you can take the water level in that tube and get the psi, and then and times 2.31. That gives you your feet ahead. So an inch of mercury equals 1.13 feet ahead. So These are some conversion factors. Um, Once again, accurate TDH calculation is critical for energy efficiency determination. Okay, so our calculation example analysis, this is just basically a little example here. So we got some test data. We have a flow of 445 gallons per minute, a suction of 3 inches of mercury, vacuum, discharge of 25 psi, and an input power of 1.3 horsepower. So our calculation steps are to calculate the total dynamic head. So our inlet head is 3 inches of mercury times 1.13 foot per inch equals 3.39 feet. Our outlet head is 25 psi times 2.31 foot per psi. That gives us 57.75 feet. So our total dynamic head is 3.39 feet plus 57.75 feet gives us a total dynamic head of 61.14 feet. Now we want to calculate our water horsepower here. So our flow times our total dynamic head divided by 3960. So that's 445 times 61.14 divided by 3960 gives us 6.88 horsepower. Now we calculate our wire to water efficiency, which is percent. So our water horsepower divided by our input power times 10% or 100% is, and that gives us 6.88 horsepower divided by 11.3 horsepower times 100. And that gives us our wire to water efficiency of 60.9%. So industry average, right around 70%. So you're in that range, but 60% really is is pretty much acceptable. You start to get much below 60%, and now you're getting down into the unacceptable range for wire to water efficiency. So, but basically, what we got now is we have a baseline, and then as we measure this, we can track our trends once again, and that's important. Single numbers, they can tell you if you're within range, but you don't know what your trend is. You really want to keep track of these as a trend, and that's going to give you a lot more data to work with. If you're a data driven organization, then data driven utility, then you're really going to want to take this data and make it useful by tracking the trends here. All right, so how to interpret the results. What's a good efficiency? So for new, well-designed systems, we're looking around 70 to 80%, maybe higher. But once again, since these are a product, then you're not going to get too much above that. So for older systems, you're probably looking 60% maybe acceptable. It depends on the pump type, the age, and the application. So and context manager matters. Compare it with the manufacturer's curve. So you should have data from the manufacturer, historical data for the same pump. Those are the trends we're talking about, and compare with industry standards. So there's 3 ways to actually look at this data. So when to be concerned? When your efficiency drops below 60% on a wire to water efficiency, now you're starting to see that the pump may be having some issues you're going to have to address and figure that out. Or there's a significant deviation from our historical trends. Once again, this is tracking trends so we can see where we're getting deviations. And so if you start to drop a lot, all of a sudden, you got generally a downward trend and you start to drop all of a sudden, then that's something you're going to have to dial in and kind of figure out where the problem is. So if efficiency plateaus or declines, now you need to start looking at that as well. So, and remember, trends are what's important. Single measurement is just a snapshot. The real value comes from tracking trends. That is the true hallmark of a data-driven water utility. So, efficiency trends reveal early problem detection, optimal maintenance timing, performance verification, and energy optimization. So, and here's just comparing a single data point versus our trend here. We can kind of see the perspective, and we got a downhill trend here versus that single data point. It's hard to interpret that sometimes other than comparing to industry standards. But if we see where we are on this line, then we know what our trend is, and we can start to see when we're going to decline below 60% and how long that took and when we need to do overhauls or replacements. All right, so benefits of tracking efficiency trends. We're looking at early problem detection. Efficiency decline is an early warning of wear, allowing for intervention before failures occur. So this actually can be part of our predictive maintenance program. And this is really what we urge people to go to is not just scheduled maintenance, but really getting into predictive maintenance. When you're tracking trends like this, now you can start to use that data properly to do predictive maintenance to estimate failure times. And then you're going to be able to get to problems before they become critical. So this is important. Um, Scientific maintenance planning. So the data driven approach to scheduling maintenance based on actual performance data rather than guesswork. We always used to use guesswork, mean time between failures, and things like that. Now we're actually doing predictive analysis to see when we might have failure, so we can address any issues long before we actually have failure and real downtime. Performance verification. Compare current efficiency to baseline to confirm if your system is operating as designed. Identifying condition changes. So if you got changes in your trend, that's going to tell you that you may have some issues. You can also see changes in well characteristics like water level decline or mineral accumulation that may indicate issues that need to be addressed by well rehabilitation. So once again, the trends are what's important, but ultimately the wire to water efficiency is going to get us at energy optimization. So long-term data helps us identify energy saving opportunities through operational adjustments. So we're going from reactive maintenance to predictive maintenance is really what's going on here. So prioritizing testing efforts. So what we want to do is we want to look at high level energy intensity assessment. So we want to calculate the energy intensity for each pump. So what we're looking at is kilowatt hours per million gallons of water. So our monthly electricity divided by our monthly flow gives you kilowatt hours per million gallons. I like to do kilowatt hours per gallon, but it gets you at the same number, and that's going to tell you your energy efficiency. Once again, you're going to have to make sure that your meter does calculate specifically for that pump, and you're not, calculating in another number of other draws on your electrical system, and so that becomes meaningless. So you want to have things metered so that you can actually calculate what's being used at that pump. That's just good practice anyway, because that's going to allow you to do pretty effective wire to water efficiency calculations. So benefits are it identifies the energy hogs first. So what's using the most energy, quantifies savings potential and justifies resource allocation because we know where our energy hogs are. So other consideration factors when you're looking at prioritizing testing efforts are long runtime, pumps running 24/7 or during peak periods should really be looked at as a higher priority. Pumps requiring regular repairs, so frequent maintenance. You're going to want to look at those because there's got to be some reason why they need frequent maintenance. High power ratings, pumps with a power rating of greater than 40 horsepower. Those you stand to gain more energy efficiency by really looking at optimizing those pumps because they're drawing a lot more electricity. And critical task pumps. So this is the old likelihood of failure and the consequence of failure calculations. So you're looking at your most critical assets here. And so your pumps that are most critical to your system and are essential for system operation, you're going to want to look at those on a regular basis. So target your testing efforts where they'll have the greatest impact. All right, taking action, energy efficient measurements. Um, there's really a number of ways to go and some different costs here. So actionable measures to improve system performance, lower no cost, adjust control strategies, VFD speed settings, open throttle valves, clean clogged suction filters. These produce quick wins with immediate impact and virtually no cost to you. Medium cost, impeller trimming or replacement, replacing worn rings, motor upgrade to high efficiency. So these are going to be short-term investments that are going to have an actual ROI to them because you're going to have improved efficiency. And higher cost is a new pump matching the system curve, and and this is really matching your VFD, matching your pump to your actual output use, so you're within that specific range instead of trying to make something fit that's going to be inefficient from the very beginning. So this is a long-term strategic improvement. So the implementation strategy, we want to start with the low-cost measurements because those are quick wins, and then evaluate if the medium cost improvements are needed, and the higher cost measures only after thorough analysis will show that you're really going to get significant benefits from those, and you are going to get an ROI for those. All right. So, best practices for field testing. The safety first, obviously, you want to use lockout, tag out procedures where appropriate PPE, insulated gloves, and safety goggles. So it's always safety first, and I'm sure most water utilities have their safety guidelines, but we always want to emphasize that data accuracy. Make sure all instruments are calibrated before testing. It really doesn't do any good to have an instrument that isn't reading correctly. So you want to have everything calibrated before you test. You want to allow the pump to run at least 15 minutes before you do the testing for it to reach stable operation. Testing right when it first starts up, you're going to get erratic. You might get peaks and valleys, and that's not going to give you an accurate test. So, running about 15 minutes will allow things to stabilize and allow you to get the most accurate measurements. So, you want to collect at least 3 sets of data at each test point to make sure that they're all within range and repeatable. Uh, Proper installation, install a power meter on the line side of the VFD, not the load side, so that you get an accurate measurement there. Ensure proper positioning for accurate flow measurement, and use appropriate pressure taps for total dynamic head calculation. So, once again, the proper installation of this instrumentation allows you to get accurate measurements and really be able to calculate your efficiency most properly. So, and people in baseline listen to operators' insights about daily operations. They're the ones out there on the line, and they can kind of pinpoint things that are going wrong. Uh, don't fix problems before collecting baseline data because you're going to want to. Sometimes we jump to conclusions to spend money we don't have to. So we really want to make a sound decision. Document all observations and data clearly for future analysis. Once again, this is part of being a data-driven utility. Is we want to have this data, we want to collect the data, we want to use it, we want to put it in a usable form so we can go back and track our trends. So, test first, fix later. Purpose of baseline data is to establish a clear picture of your system's performance before making any changes. All right. Standard operating procedures. We want to establish these so that we're consistent from measurement to measurement, so that we're always doing it the same. So, uh, institutionalized wire to water efficiency monitoring. So, you're going to want to develop a standardized operation procedure, SOP, that ensures consistent, accurate data collection. So, the key elements of this SOP are going to include your safety protocol, your testing methodology, your data documentation, and your trend analysis. So you're going to want to keep this data in a form where you can analyze the trends. Once again, the most benefit from the data is derived from looking at the trends of this data. So here's just an example monitoring log. You can see we got our date, we got our pump number, the flow, the total head. That's going to be total dynamic head, input power, and our efficiency, and then any action that we might need to take. So now this can actually flow into your asset management plan and allow you to properly manage your assets. So the benefits of standardization transform. I think there's a problem into efficiency has declined 4.3% over 6 months. Action needed now. That is the true hallmark of a data driven water utility. All right, summary. Wire to water efficiency is a comprehensive key indicator that connects invisible energy consumption with tangible water output. So we don't always see our energy consumption, but when you're doing these calculations like wire to water efficiency and our kilowatt hours per million gallons, now we're starting to see how that connects back to our energy usage, and we start to get at where we can become more efficient. These days, water utilities are trying to squeeze every dollar. They hate to go out and ask for rate increases. So if you can become more efficient, if you can reduce your costs, then you're really going to make more efficient use of the capital you have on hand, and may have to delay and maybe even delay those rate increases that you might have been thinking about because you have become more efficient. That is the beauty of becoming a data-driven water utility, is you're going to see big jumps in productivity and efficiency that is going to translate in some real dollar savings. So uh, comprehensive performance indicator, wire to water efficiency, measures the entire pump's performance, including motor, pump, and control equipment, gives you cost control, so direct impact on energy costs. Every percentage improvement can lead to significant savings, like we said. Equipment health, this is part of your asset management plan. Efficiency trends reveal developing issues before they become costly repairs. That's where you save your money, is before things become critical and much more expensive to repair, you're taking actions before they become a critical problem. The calculation method requires accurate field data, um, the flow, the head, the power, but the calculation itself is pretty straightforward. You just need to have accurate data. So make sure your instrumentation is calibrated so that you're getting that accurate data you need. And once again, I I'm been emphasizing this as we go along. The trend tracking is really what's important here. The single measurements are just baseline. The true value comes from tracking changes over time. That helps us in our decision making. And once again, we're doing data driven decisions. This is part of our data driven water utility, and we're making decisions based on actual data to guide and optimize our operations and plan our future investments. All right. That is our wire to water efficiency calculation. Um, please comment in the comments, like and share if you like this. We're trying to bring you more of these useful tools as we look at more tools to really help you become a data driven water utility and improve your efficiency and your cost savings. And that's really kind of our goal here to do that. Please feel free to contact me if you're looking, if you got any direct questions. But the comments, and I answer all the comments on the YouTube videos. So feel free to comment there. Thank you very much, and we will see you in the next show.